All right, paired sample t-testing. So just to review, hypothesis testing we did so far, a set statistic, a set test, a one sample set test where we're drawing a random sample from the population and we're comparing the sample mean to the population mean or any other reference value using the standard deviation that we have given from the population. We are doing a one sample t-test by utilizing the t-distribution by basically estimating, utilizing the principle of the t-distribution, the standard deviation of the population, using the standard deviation within the sample. The difference is arithmetically different by dividing now the sum of squares for the estimation of the standard deviation of the variance by the degrees of freedom rather than the sample size. Simple, easy, and this is how you conceptually estimate the standard deviation of the population. So now we're continuing this a little further because the one sample t-test compares one sample, the mean of one sample, to the mean of the population. Now we're going a step further because now we're comparing samples versus samples. And the simplest of all sample comparisons. So the problem with two samples is you have two standard deviations, right? So that's problematic, as you can imagine. And the independent sample t-test, you're not going to like that one because that's a little bit more complicated to calculate because you're dealing with two different variances.
Do we do anything with the population?
Well, we're not doing the comparison to the population at this point anymore. No. Population statistics is just basically setting the stage to move into samples. As you know from the quizzes and from what we discussed in class, you're basically only studying samples because they are accessible, right? Populations are hard to access, and to get an estimate from a population, you would need to do a census, which you know is done in the US, for example, as one of the largest censuses in the world. Census is, what's the plural? No, census, it's a U declination. Census, and one of the largest censuses in the world is the US Census, which is done every 10 years. And that's a major effort. There's a major budget for that. They're hiring people for doing this census. So there's a lot of effort that goes into this. So samples is what you can study to study the dynamics that you expect the population to show as well, reflected within a smaller sample, which is a subset of that population. Good. This being said, we have discussed different study designs, how you can study dynamics in a sample that you utilize to assume it will have the same dynamic in a population. We've discussed two different study designs. One is a within group design and a between groups design. And between groups design is particularly the important one because that's the highest level of evidence where you basically have a randomized setting. You randomize between an intervention group and a control group. And you study the differences between those two groups after implementation of an intervention, whatever the outcome may be. It could be hospitalization, can be deaths, can be mortality, can be blood pressure, cholesterol, you name it, mood, behavior, whatever. So outcomes that can be studied can be in a randomized setting, be studied between two groups, between two samples that allow for you in a randomized setting to minimize confounding and to study dynamics that you assume the population will show as well. Good. So a little bit of an easier design is the within groups design. In a within groups design, I briefly mentioned it, you do a lot of correlational analysis because you see changes over time and you see changes in another variable and you correlate these changes. That's a very simplified way of looking at this. A very typically within groups design is where you compare using a paired sample t-test that we will discuss today, a before and after situation. Let's say you have a behavioral intervention that improves the mood of a participant. You have an estimate of mood before he or she enrolls in your study, and you start the intervention, and then you study it again after you place that intervention. That's the simplest example. And for this comparison, you have two samples. You have an estimate of the mood before, and you have an estimate of the mood after, but it's the same individual. So what can you do logically to test whether there's a hypothesis or not? So think what we did with the one sample C test and the one sample T test. we compared a sample to a population mean. So we compared one number, one mean, to another number, to another mean, and we had estimates of the variability. So we created differences from the sample to that one constant, which was the population mean. So we got a distribution of differences. So and this distribution of differences of each individual entry in your sample to that constant of the population mean, we basically used for hypothesis testing. And we saw whether the probability of this sample distribution and this distribution of resulting differences would, under the assumption that the distribution of sample means distributes associated with the population standard deviation, whether this probability that this differs is or does not differ under the null hypothesis is smaller than 5%. So now essentially we're still dealing with differences, but now the differences are before and after. So now you have a sample of, let's say, 20 people on which you placed an intervention, and you have a before estimate of the mood, of the blood pressure, of the cholesterol, of whatever. And you're following these individuals to an after condition. So you get two different samples, but each participant in that sample contributes a data point before and one after. So you can calculate these differences that before were from your sample to that constant of the population mean. You calculate these differences now between those two samples. Calculating participant 1 after minus participant 1 before. And you do that for all 20 participants, you get a distribution of the differences. It's as simple. Conceptually, it's a little bit more complicated, but also not really. But it's a simple concept, and it provides a good starting ground for the independent sample test that we do next time. So now essentially what you're looking at, you're not looking at the distribution of the means anymore. You're looking now at the distribution of the differences between those means. So this being said, the paired sample t-test, or as a synonym, also called the dependent samples t-test, is now comparing two means for a within groups design in which every participant is in both samples. So you have differences, and you, based on the standard deviation of the differences, you're estimating what your distribution of these mean differences would look like. This is how you derive your standard error of the mean differences. And you use this for hypothesis testing. So basically, yeah, it can be used to analyze the data from many studies, because before and after scenario is considerably easy to envision, right? So you have any intervention of interest, and you have any observation of interest. It doesn't even have to be an intervention. It can be just data from 2019 to 2020, and you just want to see changes over time, and you want to see whether there was a significant improvement of whatever parameter or variable you're interested in between two times. What this means, can be used to make before and after comparisons. What this means essentially for the final, and this is where I keep on saying it builds on each other, because now what will prompt you to think of a dependent sample t-test on your final or on the quizzes is that you have a chronological order in which your sample is appearing or is being presented in your question. So you read the question, you see what is the characterization of your population or your sample population. If it says it's the same population before and after, you have to automatically think of a dependent sample t-test, which not necessarily is true, because there may be some tricky questions in there which ask you before and after, but you're still comparing two samples. So you need to kind of practice to read from the question, what is it actually asking? So, but generally, if you have a before and after condition, you should a priori think of a dependent sample t-test, because you're comparing two different chronological conditions. Okay, any questions? I see a question.
Wait, what would you do in that case? With the before and after?
You think of a dependent sample t-test. So it's a paired sample t-test. That means you have paired samples. You have a before sample and you have an after sample.
Like pre-test and post-test.
Pre and post is a classical indication for the dependent sample t-test. Yeah, it's as simple. So essentially how you do that, you create the distribution of mean differences. So you basically, how you think of it, you have two samples and you randomly pick out a sample from before and after. You calculate those differences, you drop them back into your samples, you have one mean difference. And you do that repeatedly and you get mean differences that creates your distribution of the mean differences. So if you do this repeated over and over, you get a distribution of your mean differences that could look something like this. So now basically, when you think about it, what would be your null hypothesis? If you have, under the null hypothesis, no change from before to after, your difference is going to be 0. So your null hypothesis is that before minus after equals 0. And you're basically utilizing this distribution of these hypothetical mean differences to basically utilize the principles of hypothesis testing, standardize this distribution of the mean differences according to the standard error of the mean differences. And then you basically find your critical values. And here you go and you have again tested for an hypothesis. So the steps are again identical. And the key is you really identify populations, distributions of assumptions. So the assumptions are always the same for T distribution, which is normal distribution, independent sample, in this independent samples that you have drawn, and yeah, the normal distribution.
Isn't this the same for Z-test?
It's what?
Isn't this the same steps for the Z-test?
It's always the same steps. Yeah. It's the 6 steps of hypothesis testing. The only thing that changes are basically step 1 and step 2. But the rest, you basically, when you determine the characteristic, you need to know what your comparison distribution is. Are you comparing the distribution between the sample means? Are you comparing the distribution of the differences? Or are you comparing later the distribution of the mean differences for the independent sample t-test? You just need to know how to employ the right methodology. But the steps are going to be the same. Okay, so first you identify the populations, and this is where it's important that it's one population before and after, right? That's the key. The distribution, whether it's the distribution of the mean differences or the sample means, then you test for the assumptions. You state the null and the research hypothesis, where the null hypothesis is that the mean difference between before and after is 0, whereas the research hypothesis is that it's different from 0. You determine the characteristics of the comparison distribution. You determine critical values, which are again coming from the t-score table. Lastly, you calculate the test statistic and then you make a decision. Same principle. So now we have an example here. So psychology researchers hypothesize that when mental illness is suggested as the cause of a violent act, people pay a particular attention to that suggestion, and it's important even inflates over time. That means that there's a difference in the perception whether it was a violent act before and after. So if you ask them again a week later, you will have more likely a participant in your survey reporting that it was likely a violent act that associated with mental illness. When no cause is indicated in the news report, we draw on our existing beliefs, which often include the stereotype that people with mental illnesses are violent. Good. So we have two populations. It's not really two populations, it's actually the same population, right? It's the same population, so they're recalling the details of the article just after reading it. Then give them a week to think about that and forget about the main bullet points in the article. The only thing they will take home and they will remember a week later is likely that it was associated with mental illness. That's kind of the research question. Is that true? Is that not true? So the distribution is here a distribution of mean difference scores. So these mean differences before and after. Where it's getting tricky is when you think about, so you have an independent variable, which is, I don't know, the probability or the scoring or whatever you want to look at is the independent variable. That's on the y-axis, but no, it's the dependent variable. And the dependent is time, which is good. Oh, that's a little confusing. Now that's not what they mean. So the dependent variable is still time. It is still the perception. Why is it time? Why would they say it's time? So the dependent variable is basically on the y-axis. So disregard that, disregard what's written here. So the dependent variable is the perception over time. The independent variable on the x-axis is time. It's before and after. The way they are phrasing it here would be that you ask them at different time points and you would make time the independent variable. I'm not sure why they're saying this here. In any way, so dependent variable is the perception where there was a violent act associated with mental illness. The independent variable is here time before and after. So the problem is now that you don't have a random selection. That means you need to be careful with generalization. And you also don't know whether the population is normally distributed. Overall, the null hypothesis is now people who recorded the details just after reading it, or reading the article, will have the same mean level of belief that mental illness caused the violence as people who recorded details 1 week later. So you have mu1, the mean 1 equals mu2. So that's before sample equals the after sample. People who record the details of a news article just after reading it will have a different mean level of belief that mental illness caused the violence of people who record the details 1 week later. So that would make it before is unequal to after. So now we have a spreadsheet on Canvas that serves as today's example. And it's essentially simply to be approached in the same way. So psychology researchers hypothesis on mental illness suggested as the cause of people declined the suggestion. In Chance and Yano study, participants read a news report about a deadly assault that it either did or did not mention that the perpetrator suffered from schizophrenia. They asked.
Download as a PowerPoint. How do I share this out?
So there, no, there's an Excel too. There should be an Excel and 2 PowerPoints.
Oh, got it.
Okay, sure. So they asked participants right after reading the article to write down what they record about the story and gave participants a score between 0 and 1, with 1 suggesting a higher probability that mental illness was a cause of violence. A week later, participants again wrote the recollection and received scores between 0 and 1. So these are then essentially the scores before and after. So you have here a before and after condition. What you need to do now, and this is a little different because now we need to actually first calculate differences. So that's the first action item. So you need to calculate the differences after minus before. And you're calculating after minus before for one reason, and that's a very common question being asked in the context, because there's a reason why you calculate after minus before, because if I have after a higher level and I subtract after minus before, it gets positive when it increases. In most cases, this is the most intuitive way to look at this. In other cases, there are some particular cases where you would do it the other way around, but in most cases, most intuitive is that approach.
How do you extend that, or you just do that for?
You just expand it. So now when you look at the calculation, so you get now a mean difference of 0.2. So the mean difference of this is again the average of all these entries, right? So that's our mean difference. So that's the mean difference from after minus before. So there was an increase. So following along with the alternative hypothesis, it seems to be that indeed there's an increase from before to after. So now you need to understand, was that significant? And that is once again just done in the same fashion. So we do x minus m. So we're calculating the individual difference, notably the difference. We're calculating now the variability of the difference. We're calculating the individual x, the individual difference minus the mean. This we need to log in with the dollar sign as usual. And that gives us essentially a distribution of the deviations. So now we need to, as a next step, we need to square this.
Wait.
So now you get a squared.
Yeah, wait, can you do the x minus m again?
X minus m is C3 minus dollar C $9.
5%, and you extend that.
Yeah, and then you,
Right.
no, there's something off in your calculation now. It's C3 minus dollar C $9. Do you have the same equation? C3 minus dollar C $9.
Oh, down.
Oh, yeah. Yeah, the dollar, that's a disastrous mistake. Okay.
How do you square it?
With the little head, 2.
How do you do that for, like?
You do dollar, you do D3 squared. So next step, sum of squares is calculated as the sum of these squared deviations. And now we need, as the only step, we do need to calculate the standard deviation.
How do you do sum of squares?
Sum of squares is the sum of these squared deviations, just SUM. So now we need SQRT of the sum of squares divided by, we have a sample size of 5, so we do 5 minus 1. And that gets us to our standard deviation.
Wait, you do SQRT, and then what number are you using?
SQRT, wait, hold on, let me copy it over.
Make it bigger, or?
Yeah. It's the square root.
So it's the sum of squares.
The square root of the sum, the sum of squares divided by the sample size minus 1. So it's 4. That gets us to the standard deviation. From the standard deviation, next we need to get to the standard error of the mean of the differences again. And this essentially is the standard deviation divided by the square root of the sample size, which is now 5. So that's 0.06. 0.063. Yes.
So for the standard deviation, you do n minus 1, 5 minus, you do the 5 minus 1 because the population is less than 30.
Exactly, it's less than 30, and we're doing a paired sample t-test.
So after the standard error of the mean, is that just not the equation? You don't do n minus 1.
We don't do n minus 1. So that's actually very important because that's a commonly found confusion. That's actually very central. You use the degrees of freedom here. That's 5 minus 1, and use the sample size for the calculation of the standard error of the mean. There are many tricky questions in the quizzes, and in those questions, don't confuse those two.
So standard error for me, you go to the freedom.
Correct. You use the sample size. So from now on, it's easy, right? So we're setting the alpha level at 5%, as we always do. We are now essentially, as the next step, we are defining the null hypothesis. H0 equals, that is M1 equals M2, or M before equals M after. And the HA would be M before is unequal to M after. So it's essentially, it's as simple, right? So now we have the standard error of the mean. Now we can calculate, and now it's becoming, so now we want to know the critical values. If you have a sample size of, and for that we need the t-score table. So you need the t-score table from last class. And now just as a recap, how to read the t-score table. So we have a two-tailed test because we don't know whether it's increasing or decreasing. We have this not in our hypothesis. So this is not a one-tailed hypothesis. So we're using two-tailed. We have set the alpha at 5%, and we have a sample size of 5. So if we have a sample size of 5, our critical value is 5 minus 1. That's our degrees of freedom. And we're again at 2.78, which was the same as the example last time. So it's again the same critical value. So 2.78 is our T. T equals 2.78.
And that's before.
No, that's the T. That's the critical T.
Because that's before, that's your critical, like it's n minus 1.
That is n minus 1, yes. So we have sample size of 5 gives us 5 minus 1 gives us a degree of freedom of 4. Yeah. Yes.
So if you're on the graph, say you're showing a graph, that would mean that the critical region would be the 2.78 on the positive side and negative 2.78.
Correct.
In either of those, then you would project the null.
Exactly. It's exactly this graph, right? So now it's so the distribution is now the distribution of these differences. And you're characterizing this distribution of the differences under the assumption that the distribution of the difference at the mean of the differences distributes around a mean of 0, which is the null hypothesis. And you basically, you see where the actual difference is. If it's beyond your critical value, then you reject it.
I'm confused with the differences between one. How do you know when it's a one tail and how do you know it's a two tail?
If the question, or if your research question has a directional hypothesis involved.
Oh, so if you say, oh,
So
it's going to increase.
if it's increasing and your hypothesis is an increase, your null hypothesis, is it decreasing or is it the same? And if it increases, your null hypothesis is different. In that case, you would choose a different t-value, because now your t-value would be 2.13. So as soon as your t-score exceeds 2.13, you would reject your null hypothesis directionally, depending on the null hypothesis, whether it's negative or positive, depending on your directionality. Yeah. All right. Good. So our critical value is a t of 2.78 for a two-sided test. We have a standard error of the mean of 0.06. We're calculating now a t-score. which is essentially is calculated as our mean difference minus what I was subtracting it from. What's our null hypothesis? Remember when we calculated and we tested the hypothesis of an x or a mean, an m, from our population mean, our mu, it was m minus mu. What is our mu now? And that's the $1 million question. Because our mu now is 0. Because this is your null hypothesis. So now the equation essentially, so conceptually it's minus 0, right? Divided by the standard error of the mean, divided by this. So now what is the consequence of this? So if you're subtracting nothing from something, only something is left, right? So essentially that 0 drops off. Exactly. So you only take the difference and you standardize it according to the standard error of the mean.
But why do you choose 0?
Because that's your null hypothesis. You're subtracting your null hypothesis from your actual difference.
So I guess 0, and then what's your field left?
C9 minus 0 divided by E11, that's the standard error of the mean. So essentially it's as simple as the difference divided by the standard error of the mean. When is it not that simple? And that's the trick question. And you will see a couple of questions in your finals.
C9 minus 0, the divided by?
It's divided, yes. It's divided by E11. That's the standard error of the mean. And there are some tougher questions in there. You remember how we talked about
It's always 0 now for the.
it's always the null hypothesis.
So why does the null hypothesis not 0?
Well, if you have an anticipated change. Examples that you will see in your quizzes that I can recollect ad hoc now would be you're looking at fetuses, for example. You look at toddlers or babies that follow a certain growth trajectory, and you have an anticipated change over time. And if you want to see whether a kid or a toddler did not thrive and did not grow according to what you would expect the toddler to grow, this what would be 0 here would be the anticipated growth, because this becomes the null hypothesis. Make sense? If your null hypothesis says like it's not 0, it's not 0.
Why is it 0 in this case?
Because the null hypothesis says that there's no difference. If in case you have something where you have an anticipated change, then it would be more like H0 would be M before is greater than 0. It would be M before or M after minus M before is greater than 0.2, for example. So what you would need to do then is you calculate the differences and you subtract your null hypothesis, which would be 0.2
Minus 0.
from your differences. Yeah. No, your differences from that anticipated change.
Would it be C9 minus 0.2?
That would be C9 minus 0.2, yes. Yeah. So we'll take this out because that's not the question. But this is how you would deal with that. So keep that in mind when you face questions like that. You will face questions like that. There's a good chance you will. Good, so that's the t-score. What else do we need? We're also interested in understanding the confidence intervals, because the confidence intervals here, logically, if the 95% confidence interval of your sample does not include 0, there was a significant change, right? So if you calculate now 95% confidence interval, which we can do quite easily by saying 95% CI, LL, UL, we're doing mean, which is here 0.2, minus 1.96 multiplied by, oh no, 2.78, yeah, multiplied by the standard error of the mean, gets you your lower limit. If you do now mean plus 2.78 multiplied by standard error of the mean, you get the upper limit. What becomes obvious when you look at these two numbers? What's the most prominent feature that these two numbers have?
They're the same thing. No?
They're the same thing as, well, that's maybe.
What do you mean common feature?
Hmm?
What do you mean common feature?
So are they positive or negative? So do they include the zero or not?
No.
Exactly. So you're confirming your t-score. So the 95% confidence interval is actually the most elegant way to explicitly show that the difference did not include zero, and thereby is significant. You will actually, if you write a paper and you want to compare exactly that, you don't even need to state a p-value. You just need to show the confidence interval.
What would it mean if you got a t-score that, let's say you got a t-score that was negative and you got this confidence, that would mean you did something wrong?
If the t-score is negative and the confidence intervals are positive, then something would be wrong, yeah.
Wait, how do you calculate the upper limit?
By mean plus 2.78 multiplied by the standard error of the mean. So that's,
The fact that it doesn't go through zero, what does that show?
that zero is not contained in the 95% confidence interval shows that your null hypothesis, that your mean difference is identical to zero, must be wrong at an alpha level of 5%, which is your acceptable type 1 error. So your type 1 error risk that you're rejecting a null hypothesis that there was actually no change is wrong with a certainty of less than 5%. Yes.
So you reject the null hypothesis?
You reject the null hypothesis and you're, I guess, something like 3% certain that you're not committing the type 1 error. You're 97% certain that you're not committing the type 1 error, 3% rest risk of having type 1 error. Sorry, misspoke.
And if the lower limit was negative, let's say, and the upper limit was positive,
That's impossible. Huh?
that's impossible.
Mm.
So
Think
then-
about it. Think about it. You have just rethink that, because that's important conceptually. It cannot be, because the lower limit is always going to be lower by definition, because you're
if the
subtracting
lower
it from the
was
mean.
negative,
The lower one always needs to be smaller than the upper limit.
so that would be negative.
If the lower limit would be negative, it would contain the zero.
Yeah.
And
lower
then
limit
it's
negative.
not significantly different. If you used a critical value of corresponding to an alpha of 5%. All right. Good.
Let's say we use an example where the null hypothesis was not zero, like the 0.2 example.
Okay.
So then it would have to pass that, like you have to pass that to.
So it would mean that 0.2, if you want to, or if you are, if you're thinking that your hypothesis is, your null hypothesis is not true, and your t-score is greater, with the calculation where you subtracted here 0.2 rather than 0, your 95% confidence interval would not contain the 0.2. That would be the approach. Okay. It's not too complicated, but conceptually it's opening up, because once we do the independent sample t-test, And we will repeat this next week when we
So
do the
if
revision.
if it doesn't contain your, like, that number, the 0.2 or 0, then you reject it.
Correct. Good. Lastly, we also want to calculate an effect size. And you guessed it, it's calculated in the same fashion. So we're calculating now our mean difference minus 0 divided by the standard deviation. That was something wrong. Minus 0 divided by the standard deviation gives us an effect size of 1.4.
Sorry, can you flip over that?
Yep. Very good. Yes, it is. It's the effect size of, oops. It's an effect size that is large. Yeah? So we have 1.4 effect size. So that's how you would approach a dependent sample t-test. And it's not a difficult test. It's just conceptually, it goes even further into hypothesis testing, because it's the first time we're dealing now with two samples. Although they're the same sample and therefore arithmetically quite simple, you're rejecting the null hypothesis. Yeah. So we did the 95% CIs. So here we have the 95% CI. So we have 0.2 as the mean. We have our 95% confidence intervals, and the 0 is somewhere here. That's this. So Cohen's D is 1.42, which is a large effect size. 1.4. What? Somebody did a lot of rounding here. So they rounded quite massively. That's why they have a different D.
What was your E10 for the?
E10.
Yeah, for.
E10 is the standard deviation.
Okay.
So remember how you have the difference. If you have a set test or you have a one sample t-test, you calculate those differences and divided by the standard deviation gives you the effect size. Now you have the same calculation. You calculate the mean difference, you subtract your null hypothesis from it, which is 0. In our case here, you divide it by the standard deviation, you have your effect size. And yeah, with 1.4, you actually have quite a large effect size. Why do you think that is? Because you have relatively little variability, right? There's not really much variability. These are all around 0.2. So there's variability drives them. Essentially, the decision whether the effect size is large or not. At 0.2 with these decimals is quite a large effect size, right? And again, just to recap what the effect size is, the effect size takes the effect of variability out, because variability is affected by the sample size, takes this out, and basically puts the emphasis back on the difference. Good. All right, so this is this. What else? Because there are two more topics that are a little bit tricky now. Okay, is this so far clear? I think it's considerably simple, right? I don't think it's really complicated. And just go through it again conceptually, or we can do another example. Yeah, we should get to another example actually. It's conceptually, once you have understood it conceptually, it's arithmetically, it's a stroll in the park. Good. Order effects. What is an order effect? An order effect is, let's say you have an intervention where you try to improve in a population of people with a diagnosis of major depressive disorder. You try to improve their mood by have them walk a puppy for, let's say, an hour a day. And you're comparing their mood and their improvement from week 1 to week 2. So now you see this improvement. And now you study also the comparison from week 2 to week 3. So they already had kind of an effect of that puppy walking in week 2. So the order in which the intervention is being implemented plays a role. So if you had an intervention before, your mood is different. So order of placing the intervention makes a difference in how strong the difference is, and how much of a significant difference you will see, how much treatment effect you think your intervention will have. So for that very reason, these order effects is, so the participant's behavior changes when the dependent variable is present for a second time. So there will be less effect of that intervention. So the dependent variable here would be the puppy walking.
How would there be less effect?
Well, because you had already effect the first time. So walking the puppy for week 1, and then you.
Is it possible though that it has an increased effect because?
Yes, absolutely.
Oh, so it's not necessarily less effect.
Absolutely. But the problem it has, it's your estimate of your treatment effect is not accurate anymore, because now that previous exposure to your intervention has confounded your difference, your estimate of the difference. And that is what an order effect is. So the sequence, the chronological sequence plays a role. And for that very reason, you have what is called here counterbalancing. And counterbalancing is where you basically you change the chronological order. Let's stick with the puppy example. I like the puppy example. So okay, so you have week 1, you walk the puppy. Week 2, you don't walk the puppy, and you compare mood week 1 to mood week 2, and you have puppy walking week 1, no puppy strolling in week 2. You have a worsened mood, right? So now you want to see whether week 0 to week 1 showed an improvement, so your mood increased. So counterbalancing would be now to minimize the effect such an order effect has, because week 2 may be affected by the puppy walking week 1. So you change the order in which you get the puppy out for a walk. So essentially you're changing the chronological order, and if you do that systematically, you can systematically minimize the effect of the chronological order. So that's minimizing the order effect. And if you even do that randomized, you essentially entirely eliminate that order effect. And you will see study examples like that in your quizzes, and we can talk about some more later. But basically, in a study design, you would basically refer to that as a so-called crossover design, and in a randomized fashion as a randomized crossover design, where basically you have an intervention in week 1, no intervention in week 2. You calculate the difference. Then you have no intervention in week 1, but intervention in week 2. You have a crossover design. So individuals crossed over from one, either having the intervention first and then no intervention, or having intervention in week 2, but not in week 1. So in randomizing participants to receiving it either before or after, will basically give you this randomized crossover design. And yeah, so this can be done on a design level when you study prospective research. Okay, so that was all essentially for the material and the concept today. We can do another example now. So if you go into the spreadsheet, you have here a simple example again is this, for example. So you have on the second worksheet, you have exam scores. You have exam scores from exam 1 and exam 2. We're being asked to calculate the paired sample t statistic for this exam course using a two-tailed test and alpha level of 5%. Identify the critical t values, make a decision regarding the null hypothesis. Assume you instead collected exam scores from 1,000 students whose mean difference scores and standard deviation were exactly the same as those for the 8 students. Using a two-tailed test and an alpha level of 5%, identify the critical t values and make a decision regarding the null hypothesis. So basically, it asks you to understand the effect of a sample size on the hypothesis test. How did change in the sample size affect the decision? Okay, good. Okay, so we're getting there. Okay, we have exam 1, exam 2. Same students, it's 8 students. First, we want to calculate the difference. We're calculating after minus before. So we're having now calculated differences from before, from after minus before. We're calculating a difference, a mean difference. So in average, there was only an improvement of 1.25, which essentially is not grandiose, to be honest, but okay, that's the example. So mean difference is now 1.25. Next, we want to know the standard deviation, and we know again how to calculate the standard deviation, x minus m. This is basically, again, this difference minus our m, needs to be logged in again with the dollar sign. And you're squaring this, so x minus m squared equals this squared. You're summing this up. Gets you the sum of squares. Now we want to know the variance. The variance equals sum of squares divided by the sample size, which we know is 8 minus 1.
Wait, sorry, can you repeat what you did for the sum of square? Oh, you just added that up.
That's just the sum of the squared deviations, yeah. Then the variance is the sum of squares divided by the sample size minus 1. And the standard deviation is the variance divided by, it's the square root of the variance. Getting confused myself already. Okay, 5.7 is our standard deviation. The consequent standard error of the mean equals standard deviation divided by square root of 8. That's the sample size. So same principle as always.
Are you gonna post this Excel sheet out there? Are you gonna post this Excel sheet out
Yeah.
there?
No worries. Okay, so basically we're now at the standard error of the mean. So calculate the paired sample t statistic. So what we're doing is now a t-score. So our t-score is calculated as always as m, which is 1.25 minus 0 divided by the standard error of the mean. We have a t-score of 0.63. If we are now using a two-tailed t-test, paired sample t-test, our null hypothesis is going to be m equal or m before equals m after. Or HA is the same thing, just unequal with an alpha of 5%. This essentially gives us a critical T of, where would I look?
Minus 1 would be 7.
Correct, it's 7, it's 2.36. So now we want our 95% confidence interval. is now lower limit would be our mean minus 2.36 multiplied by the standard error of the mean. And now it's mean plus 2.36 multiplied by the standard error of the mean. So from minus 3.5 to 5.99 is our 95% confidence interval of the differences that we have observed. Are we rejecting or accepting the null hypothesis? We're accepting the null hypothesis. We're not rejecting. Correct. So what happens now? So we are rejecting the research hypothesis, we're accepting the null hypothesis. If we had now 1,000 students, how would we calculate this? Same standard deviation, same means. How would that be done? What's the difference? Same standard deviation. So that's the same. Okay, so this is now D. Okay, 1,000 students. Plural. So 1,000 students, what's the same? Standard deviation remains the same, right? Who said? The mean is the same. Mean as D. What changes? The standard error of the mean changes. Because the standard error of the mean is calculated as standard deviation divided by SQRT of 1,000. So now we have a standard error of the mean which is 0.063. So now our t-score is calculated as t-score is calculated as 1.25 minus 0 divided by 0.063. So now we have a t-score of 19. 125 minus 0 divided by 0.0063. So, and this is now the perfect example where now the effect size plays a major role because the effect size is here. So this is this C13 minus 0 divided by standard deviation. C13 divided by the standard deviation. So the effect size is the same. The t-score is substantially different. And with 19, I don't think we need to look that up on the t-score table, right? So that's the effect of the sample size. And this is what you would reject the null hypothesis now. So if you would get the same results from a sample of 1,000 students, you would reject the null hypothesis, and that's the effect of sample size. It's just bringing it's arithmetically simple.
Oh, because it's not as part of your.
Well, the 95% confidence interval would also change, obviously, because if you do a 95% CI, so you know because the t-square is larger than the critical value, right? If the t-square is 2.36, then 19 will exceed that by far. And logically, also the 95% confidence interval will decrease. So if we do the mean minus 2.36 multiplied by the standard error of the mean, in this will also substantially decrease. So this standard error of the mean makes it more likely that you reject the null hypothesis. And that's why this is important to understand the difference between effect size and the standard error of the mean. And that's basically putting it in practice. Okay, any questions to any of this? So just as a recap again, so it's important to understand when to use the paired sample t-test. You don't have a standard deviation given, and you have a before and after chronological order. You also need to understand that there's an order effect. So if you have an intervention before and you have no intervention after, in the week after, think of the puppy walking, you have a carryover effect. So that's why a lot of studies essentially have something which is called a washout period, before and after period. So that individual doesn't see a puppy for 2 weeks and then can walk the puppy again. Or alternatively, you do counterbalancing and you do intervention, then no intervention. And for the other individual, for the other half, you basically do no intervention and then intervention. That's counterbalancing. If you do that randomized, you have a randomized crossover design. I guess these are the main take-home points from the design part of it. Okay, but that's pretty much all of it. If no further questions, we can conclude for tonight. Have a nice evening. Bye.